Hey! Today we're going to talk about the scientific method. We touched on this topic in my previous videos about pseudoscience. If you haven't done so already, I recommend that you go ahead and watch those pseudoscience videos. You can find them on YouTube by searching for Deanna Beals on my channel. The big difference between something that is pseudoscientific and science is that science follows the scientific method. The scientific method is a series of steps that every scientist must follow in order for something to be considered credible. The first step is that you observe the phenomenon that you're interested in studying. Then, from those observations, you develop a question. Then you do background research to find out what other scientists have found, or if anyone has done any research on that topic. Then you develop a null and alternative hypotheses. Then you test with an experiment, and you collect data. From this data, you analyze it using statistical procedures such as a t-test or a ANOVA, an analysis of variance. Then you draw conclusions from this data where you're going to either reject, fail to reject, or refute your null hypothesis. At this point, you may have to develop a new hypothesis and begin your scientific methodology again. Once you've finished this, then you send in your results to a peer-reviewed journal where other scientists are going to duplicate your experiment and hopefully duplicate your same results. Now, when we are being scientists, we use certain definitions and terminology that a lot of times gets confused with layman's terms. One of these is the word proof. In science, we can never actually prove anything because everything is based on statistical probabilities. Even if we fail to reject our null hypothesis, there is some statistical probability that we just happened to see that and that it wasn't a result of what we thought it was. However, just because we can't necessarily prove 100% something, theories are created which are basically considered as laws. These theories they've been substantially tested throughout a long period of time, and they can still be tested today. However, all the tests that have been made support the theory, and therefore basically in science we see theory as a fact. Whereas in the layman's terms, usually a theory is a hunch or an idea or something that has not yet been tested. A hypothesis is more likely to be what the layman is considering. A hypothesis is a proposed explanation that hasn't been tested yet. But in order for something to be considered scientific, the hypothesis must be falsifiable, meaning that you develop a null hypothesis that you can basically try and prove wrong. A lot of times when scientists create a hypothesis, they follow an if-then statement. So, if I pick up my keys, then the dog gets excited because he thinks I'm going for a walk. When you're looking at building your hypotheses, you have a null hypothesis, which is written as H sub 0, and your alternative hypotheses, which can be written as H sub 1, H sub 2, so on and so forth. You can have many alternative hypotheses, but only one null hypothesis. In your null hypothesis, basically you're trying to disprove or reject or nullify your ideas. The null stands for no difference or no effect that you find, whereas your alternative hypothesis is the thing that you're trying to test. So you're looking for a difference or some type of an effect between the control and the treatment. When we run our experiment, there's a couple things that are important. The first is that every experiment has a dependent and an independent variable. The dependent shouldn't change. So that means both the control and the treatment have the dependent variables. However, the independent variable does change. So usually the control does not have the independent variable, but the treatment does. Then, after you run your statistical analysis, you would run a significance test, where you come up with a conclusion if you rejected, failed to reject, or refuted your null hypothesis. Usually, we run the significant test off of a 95% confidence level, which means that if you reject your null hypothesis, that it's 95% likelihood that the results did not fit. Whereas if you fail to reject it, your null hypothesis, then it's a 95% likelihood that the results do fit. This term significant is another term that really gets misused in layman's terms. In science, we only use the word significant when we mean statistically significant, as in we know that it did not happen from random chance alone, that it was, say, 95% likelihood that we rejected our null hypothesis. In layman's terms, the word significant basically just means something important. When we look for a significance test, basically the hardest math that you're going to have to do is find the standard deviation. And the standard deviation is just the square root of the variance. What the variance refers to is the amount of a range that a number deviates from the mean. So this mu here, that is your mean. And then you can see we have 1 sigma, which is 1 standard deviation, 2 standard deviations, and 3 standard deviations away from the mean. In layman's terms, error means a mistake. If you had several errors on your test, it means you made a mistake. You did not get the right answer. However, in science, the word error means the difference from the exact number, or basically the range. So we always have a mean plus or minus the standard deviation when we are reporting numbers. In statistical analysis, we sometimes have type 1 or type 2 errors. A type 1 error is a false positive. An example of this is if you took a pregnancy test and it says you're pregnant, but you are not pregnant. The other type of error is a type 2 error, which is a false negative. That means if you took the pregnancy test and it says you're not pregnant, but you actually are. Now we're going to talk about the differences between what is considered a good and a poor figure or table. And figures include any graphs or pictures. This is a nice and simple graph, but unfortunately it doesn't have any labels. Therefore, it is not a good graph. We don't understand what this information is trying to show because there's no labels telling us what the units are. This graph is just way too busy. It has pretty much all the data points on it, but you can't tell what kind of trends there are just by looking at it. And the whole point of a figure is you should be able to look at just the figure alone without reading the text and be able to understand the basic idea or conclusions from the research. Because there's so many data points on this one, you can't see a trend and you can't draw any kind of conclusion. This graph is not a good one because there's a bunch of lines in the background, and so you can't see the actual data point here of this downward negative trend. If the user took out these background lines, it would greatly increase the readability and clarity of this graph. Here's another one that is pretty good. It has its labels on its X and Y axes, but there are no units on the labels, so you're not sure exactly 50 what? 50 pounds, 50 yards, 50 meters, you don't know. The other thing is you see how this graph is put in to a 3D display. We don't want to use that because it looks pretty, but it's not scientific. We use a 2D display. This figure is pretty good. It has axes labeled, it has the units, it has a legend, and it has a title. However, the one thing it's missing is a description, which is just text that basically summarizes what the graph shows. Like this one. This graph has a great description. Without looking through the research paper, you're able to read the description of the graph alone next to the graph and understand the basic ideas. Here is a table that is also a good table. It has a description, a title, and labels for all the units. Here are some things to remember when you are making your figures and tables. When you are first plotting your graph, I like to remember the difference between the y-axis and x-axis, because the y-axis is vertical and has a tail just like the letter Y. Then you're going to plot your data points and decide what type of graph you're going to use. There are three main different types. A scatter plot, where you just have a bunch of data points. A line graph, like this, where you connect those data points. Or a bar graph, where you have a set of different data points. The differences between these types of graphs is you would use a scatter plot if you have a lot of information but you don't necessarily know if there's a trend or not. A line graph is used when the different data points are related to one another, and therefore there is a continuum of data. And you would use a bar graph if the data points are independent of one another. Like, let's say that these three bars represent three different experiment outcomes. Then you want to make sure to label your axes and, importantly, include your units. Make sure you have a title and a description. The description is basically text that is going to, basically in layman's terms, describe what you're seeing in the graph. So, for example, the axes label here may be time compared to distance. And the units that we're going to include maybe seconds or minutes or hours or days, and the distance may be centimeters or meters or kilometers. Now, if this is the case, a bar graph is not the correct choice, because time and distance is related to one another. So the data points here are connected in a continuing fashion. In your title, you always want to start out with graph 1 or graph 2 or graph 3. That way in your paper you can refer back to this data point as seen in graph 1. Then your title is going to describe relationship between time and distance in whatever it is you're looking at.